In this moment, or in this problem, we have a frame that's fixed at points A and B, and we're asked to determine what would be the moment caused by the force applied at point C uh, that would about the axis from point A to B. Okay, so the moment MAB is going to be equal to the magnitude of MAB times UAB, where UAB is a vector and MAB is a scalar. So we first need to determine what the magnitude of MAB is. So we know that MAB will be equal to U, the dot product of the unit vector UAB times the cross product of R and our applied force. All right. So let's define the components of this equation. All right. So we'll start with UAB. We know that UAB is going to be equal to RAB divided by the magnitude of RAB. So RAB is equal to RB minus R of A, but RA is at the origin, so it will be equal to 0. So it's just going to be equal to RB, or the coordinates of RB. So point B is at 0.4 meters in X, and it's at positive 0.2 meters in the Y direction, and it has no Z component. Alright, and then the magnitude would be equal to the square root of the sum of the squares, so it would be equal to 0.4 meters squared plus 0.2 meters squared. So we end up getting, if we divide all that through, we get UAB is equal to 0.89443 times the unit vector I plus 0.44722 times the unit vector J. Alright, so that's our first term complete. The second term of our equation R, we can define from any point on our axis AB to our applied force F. In this case, I'm going to select from point A to point C as our R term. You could also, if you wanted, you could go from point B to point C. That would be totally fine. You could also go from point A to point F as well, or this point here, I'll call it point D. That would also be acceptable because it's also along the line of action of our force. So what we're going to define here is our vector R, which will go from point A to point C. So that's equal to RC minus RA. Again, RA is equal to 0, so it's just really equal to the location of point C. So point C is at 0.6 meters in the X direction. It has no Y component, and it has a value of 0.3 meters along the Z direction. Okay, and then the last component we have is our force. So our force was given to us as a magnitude of 300 newtons, and it's just going along the negative Z direction. So it'll have no X component, it'll have no Y component, and it'll have a minus 300 newtons force in the Z direction. Okay, so now we have all of our components together. We can evaluate this equation here using the following determinant. So we know that MAB, alright, we can define this equation here. We can define using a determinant where the top row is equal to UAB, so it would be equal to 0.89443, 0.44722, 0. Alright, and then the second row would be equal to RAC, which would be equal to 0.6 meters, this 0 and 0.3 meters, and then the last row is going to be just equal to our force, which would be 0, 0, and minus 300 newtons. So to evaluate this determinant, the first step we're going to do is we're going to copy the first couple rows here. So first columns, first two columns of this equation. So so if we do that, all right. And then we're going to take to evaluate this determinant, we're going to take the diagonals here. All right. And then we'll take the diagonals going the other way. So all of these are equal to 0, and then the diagonals going in the opposite direction would be 0, except for one term here. So that for that term is going to be equal to MAB will be equal to that term. So that term, since we're going from the top right to the bottom left of our determinant, we have to include an extra negative sign. So it'll be equal to negative 300 newtons times 0.6 meters times 0.44722. And if we get that, what we end up getting is a positive 80.499 Newton meters. And then we were specifically asked to determine this moment as a vector. So we have to multiply MAB by UAB. So if we do that, we would get 72.0 Newton meters along the x-axis plus 36.0 Newton meters along the y-axis, and then there's no component about the z-axis, so it would be equal to 0 about the z-axis. All right, so to conclude, what we did in this problem is we first defined our governing equation. We realized that we had to determine MAB and UAB in order to solve it. We defined MAB using our dot product of our axis times the dot product of our axis and our moment about any point about the axis. So we define each of the terms in our vector, and once we did that, we plugged it into our dot product equation, solved for the moment about the axis, which is a scalar number, and then to define it as a vector, we had to take the scalar product of our moment about our axis times the unit vector of the axis.